Okay. Hi, my name is Chris Simpson. I work at the University of Bristol, and I want to present some work that has been ongoing now for perhaps 2 years, looking at the impact of 2D plastic constraints, so that's essentially in-plane and out-of-plane constraints on fracture behaviour and ultimately the structural integrity assessment. And the driving force for this is obviously the fact that with loss of constraints, you can significantly underestimate the fracture resistance of a component if you use a single parameter, so something like K. And obviously there are other parameters like T and Q, which look at in-plane, and TZ, which look at out-of-plane constraints, but it's typically one or the other. And then following on from that, there's obviously also some work that's been done recently, or more recently at least, which tries to look at 2D plastic constraints, so both in-plane and out-of-plane, by kind of characterising the volume of plasticity around the cracked tip, or taking contours around the cracked tip. But I think that work is still kind of in its infancy a little bit, and there's more information and understanding that's needed. And so what we've been trying to do is develop that understanding and just kind of provide additional fundamental detail. And so that comes in a couple of forms. So firstly, we want to understand the plasticity a little bit more, and also investigate and separate the strain energy release as a function of 2D plastic constraints. And so we've done that through a series of experiments which we carried out at the Diamond Light Source, which is, for those of you who don't know, the synchrotron in Oxfordshire. And we were looking at aluminium, titanium, metal matrix composites. And these were double-edged, not tension samples. And so we looked at 4 combinations. So that's 2 different crack lengths and 2 different thicknesses, or combinations thereof. And today I'm just going to talk about one sample, really kind of concentrate, not necessarily giving us a comparison between those samples, but really talking through some of the methodology, because there's been an awful lot of work and a huge amount of effort that's gone into the work up to this point. And so here you can see, so this is our experimental setup that we used, and so this is the incoming beam going into our sample, and then on the left-hand side we have imaging optics, which allows us to do X-ray computed tomography, and then just about, kind of squint a little bit, on the right-hand side there is an X-ray detector to do diffraction measurements. And so the diffraction measurements were to look at the elastic strain and also the elastic strain energy release rate, and the X-ray, so the imaging optics was for computed tomography to look at total strain and total strain energy release rate, which is kind of the aim of this, really. So yeah, like I said, just one sample is what we're going to be looking at right now. So in terms of the diffraction work, we're doing monochromatic diffraction using a 2D area detector. The image in the top right is an example of the kind of diffraction patterns that we get. The rings that we produce, and each of those rings is associated with lattice plane, or a family of lattice planes. And really what we're trying to see here is we're trying to study how the rings change with applied loads. Right? With applied loads, the lattice spacing changes, and that's essentially what we're trying to measure. So measuring the elastic strain from that. And so we were doing that work across a 2D grid on our sample, so something like 600 points we were looking at, and the point density was much higher around the notch, because that's obviously where, or the subsequent crack, because that's where we have the highest strain gradient. And so in terms of the elastic strain work, this is really the point that we're at the moment. So we have up here the 2D strain as a function of applied load, and on the right hand side there is 1D profiles taken through in line with the notch. And what you can see in the bottom left 2D map is that we have crack extension there, because that was just just prior to fracture. And really, this has been building up to the final step, which is kind of happening right now, really, which is using these maps to calculate J-elastic. This is building on work done by Salim Bali, which is work done at the University of Oxford in collaboration with Bristol, which is, well, it's a code base called JMAN. It's certainly worth looking at. I think he presented it at ECS 21, and he's had a lot of success with it. So yeah, we're calculating J-elastic, and we obviously want to compare that and contrast it against total strain energy release rate. And so we've calculated that using X-ray computed tomography and associated use of digital volume correlation. And so with the X-ray computed tomography, essentially we take about 2,500 projections, typically over 180 degrees in a synchrotron, but we were slightly limited by a load rate, and then use filtered back projection to go from that to the 3D tomogram. So what you can see on the right-hand side is a 2D virtual slice through that 3D volume, and then below that there's a stack of those here. And you can obviously see as well the crack just initiated on each side, and that's because this is at the maximum load, that 4.5 kilonewton that we saw in the X-ray diffraction work. And what's also interesting here, by the way, is that we've chosen the material, the ALTI, specifically because of this kind of texture that you can see, this inherent texture. And basically that's because we want to do digital volume correlation, which is essentially a 3D analog to digital image correlation. And to do that, there needs to be some kind of speckle or texture to the material, because obviously unlike the DIC, you can't spray or scratch that pattern onto the material. So here what we're leveraging is a difference in attenuation coefficient between the AL matrix and the titanium particle. And then we just essentially split our 3D tomogram into subvolumes and then track the displacement shifts of those flows. And that gives us what we can see here, which is our raw displacement field. And the pre-processing doesn't really stop there, so then we have to go through a process where we do outlier deletion and then extrapolate those values before using something called volumetric phase congruency, which again is another technique which we kind of had to develop as part of this process. And so this was covered in Ahmet Chinar's PhD thesis and some of the associated papers which you can find here. And basically this is an image processing tool used to characterize and define and highlight discontinuities. And although there's other techniques to find the crack within, using DIC or DBC, this is particularly robust. And so if you do use digital image correlation, I would strongly recommend that you have a look at some of that work. And so basically from the volumetric phase congruency, what we produce is this grayscale volume, like sharp grayscale volume, and then we can use that to segment out our 3D crack, which is really useful, really nice in many ways. So we can see, for example, the tortuosity of the crack, and if, for example, you have a more complex crack than we have here, you can look in 3D at the branching and texture and distribution of your crack. So, again, very useful and interesting tool. So anyway, after that process, we have our tidied up tidied up DBC data, which we can then use to find the COD, which is something that we're using and interrogating at the moment. But in terms of this presentation and this work, what we're obviously more interested in perhaps right now is using it to calculate J. So J as a function of through thickness position in this particular case. And again, this is leveraging and building on work again by Salim Bali from Oxford, who's working in collaboration with Bristol again. And essentially what this allows us to do is import our displacement fields into Abaqus, and then we use the PC-derived crack path, and we segment that out before going through a process of essentially optimizing the boundary conditions, optimizing the meshing, before leveraging Abaqus's inbuilt FE solver and the domain integral method to calculate J. So like I said before, this is J that we're doing. We're calculating J on a 2D slice-by-slice basis, so essentially iterating through all 3D displacement volume to calculate J as a function of position. And then we start to get some of the initial results from that. So here, what I've done is I've converted J to K, and you can see that in the center of our sample, we have a value of K of around 50 megapascal per meters, which increases to above 70 at the edge of the sample. Interestingly, those results are actually in agreement with some of the other work in the literature. We're fairly confident with our analysis technique, but we're going to go back and we're doing some other FE work. Potentially there might be some errors introduced by calculating J on a slice-by-slice basis through the 3D volume, because that's, are we losing some information by doing that, by not including all of the extra data? But essentially, I think it's probably to do with a lot, a decreased amount of constraints and increased plasticity at that time. And then just to kind of wrap this up, really, basically what I've tried to show here is the tools and analysis and experimental techniques that we've gone through, really, to get to this point. So there is essentially 3 or 4 different tools that we've had to develop to do this work. And the efforts are now starting to yield interesting quantitative information, and essentially what I want to say is it's almost what's this space. So in the next 6 or 12 months, we hope to have 1 or 2 papers out which kind of really delve into the impact of 2D plastic constraint. And then very briefly, what's next? So we use some of the code that we've developed to calculate the elastic strain energy release rate. We separate elastic and plastic strain energy release rate, and the current working hypothesis or hope perhaps is that J elastic might be constant with respect to constraints, and it's just a changing value of J plastic. So, yes. Anyway, okay, thank you very much for your attention.